A conglomerate such as that of the Great Slave Lake was the product of a high-energy environment, such as where the pounding of breaking waves undercuts cliffs and breaks away rock fragments of conglomerate size, especially during storms. Boulder beaches, possible future conglomerates, are common in the coves and the bays at the foot of high cliffs. The rubbing together in the surf zone soon rounds the fragments. Perfect spheres are rare, and most boulders reflect the original shape of the fragments. The sea soon sorts out the smaller pebbles, which are transported in the surf and piled into shingle mounds interspersed with sand. There's a high rate of attrition in this environment, which resembles a tumbling machine. Grains are produced as the corners are knocked off less rounded pebbles. The ebb and flow produces gently inclined beaches of potential pebble conglomerate. The sand of the medium energy environment is derived in part from the continued breakdown of pebble beaches and in part from the sand brought to the coast by rivers. The sand is piled up as smoothly sloping beaches backed by wind-blown sand dunes. Sedimentary structures in the sand, which might be preserved in a future sandstone, provide information about the water currents at work during the deposition of the sand. If the water flow is always in one direction, as in a channel or a fast ebbing tide, asymmetrical ripples form. Particles move up the gentle slope and are dumped over the steep lee edge of the ripples. This mode of ripple formation causes the sand to move forward in the direction of flow, and any object heavy enough to be stable is engulfed while the sand ripples pass over them. In a beach section, the typical form of asymmetrical ripples is easy to see. The gentle slope, having faced the oncoming flow, and coarser grains often lie in the troughs. A different form of ripple, this time symmetrical, is produced where the water doesn't flow constantly in one direction, but instead oscillates, first moving in one direction and then in the other direction. These ripples are often called oscillation ripples. Other conditions of flow and depth of water produce other ripple forms, all of which can be interpreted either in the soft sand or in the subsequent rock, if a sandstone should be formed from the sand. Ripples are not the only structures to be preserved in sediments and sedimentary rocks. Heavy rain on wet sands produces characteristic raindrop imprints. Complex and deceptive tracks can be produced simply by runoff scouring to one side of a rolling object each time it comes to rest. Tracks are also produced by animals. In this case, the tracks are those of a crab and lead to the spot where it's buried itself. A duck puddling for food produced these peculiar crescent-shaped marks. The movement of water sorts and grades the sand. lighter particles are concentrated at the swash mark, that is the farthest reach of breaking waves. Depending on the energy of the waves, shells are often brought together in small mounds. Shells which break into slivers lie in stable positions either parallel to or at right angles to the current direction, depending on their shape. Unbroken shells are usually turned over until they lie with their open side down. Although to the untrained eye there's little hint on the surface of beaches having an internal structure, there is a very clear structure of thin layers or laminae of heavy or light mineral grains sorted and graded by the surf. Most grains are usually quartz, and the larger ones form coarse sand layers. Sometimes dark, heavy minerals, such as the iron-rich mineral ilmenite, form concentrations. Such minerals as ilmenite are commonly brought by streams to the coast, and there are spread out and sorted by the tides. In many cases, such concentrations form the basis of economic mineral occurrences. The Elliott Lake uranium ore may have been concentrated in this way. Water is not the only means of transporting sand. Wind, as soon as it reaches a critical velocity, and if the sand is dry enough, can rapidly shift many tons of sand in a short while. Each particle moves along by bouncing, a process we call saltation. And ripples often form as a result. In this case, the ripples are moving from bottom right to top left. The sorting of material of different shape and density occurs just as in water. Dunes are piled up by wind and stabilized once dune plants take hold. More sand is blown in and the dunes grow. A section through a dune hillock shows cross-bedding. And that cross-bedding is at an angle that's diagnostic of wind-blown or aeolian deposits. In the lowest energy environments, protected from waves of the open sea, fine mud is transported by tides. And the most striking thing is the diversity of the fauna and the flora which burrows and destroys the laminations of the mud. Gastropods are typical, snails. The mud is thick and glutinous normally, but here and there small rocks and driftwood accumulates, and the tide brings in more mud, and mussel beds often accumulate or grow in such places where rocks and driftwood is exposed. Surrounding the mussel beds are tidal flats where ebb channels, which are constantly migrating, occur. In the process of migrating, the ebb channels rework the laminated beds, and the walls show the lamination of the tidal flats, laminated muds with occasional shells, such as this Maya shell in its living position. Cut sections show the typical color of the tidal flat muds, usually black because of the lack of oxygen in the sediment. Burrowing by worms allows oxygen into the sediment, and there the color is lighter. Once beyond the reach of salt water, algae and grasswort grow, and form the fringe of the salt marsh community.